Okay, so now to look at some inference for the slope of a regression line. So before we can actually inference, recall that in previous units, we need to ensure that our sampling distribution is approximately normal so that we can carry out these procedures. Now, in the last unit, or 7.1 through 7.3, we used a chi-square hypothesis test to determine if there was a relationship about two categorical variables. Now we will use inference for slope to see if there's a relationship between two quantitative variables. And just keep in mind it wasn't just two categorical variables. Well, one or two. Oh, you know the whole chi-square thing. It's fine. We'll figure it out. But in the same way, our shape, center, and spread for the sampling distribution of slope looks like and has the following properties. So the shape we can see is approximately unimodal and symmetric. And it can be through any of these variants here. So either the population that we're sampling from is stated as normal, the central limit theorem applies where my observations are 30 or more, or the graphical display of the residuals shows no extreme skewness or outliers. Now notice not the residual plot, but an actual graphical display of said residual. So that could be a dot plot, histogram, normal probability plot, etc. We'll keep it spicy this unit. The center is satisfied through our random condition, whether we've taken random samples or used random assignment in a completely randomized experiment or some type of experiment. And if we are truly randomly selecting, then the mean of our sampling distribution for the slope should closely approach beta, which is the population slope. Next, if I have independence through the 10% condition or other methods here, then the standard deviation of the sampling distribution for slope would look like the following. Would look like the population standard deviation divided by the population standard deviation in terms of the explanatory variable times the square root of n. Now this formula looks nasty, so we're not going to bother to really look at it or pay attention to it, but we're going to be using a lot of computer output for this unit in terms of accomplishing our inference for regression here. So again, same thing, we can see here's our slope, our random condition, our shape, and then our spread. Now, degrees of freedom, recall that since this is a T procedure, we are estimating some parameters, and typically we've used n-1. However, for this model, we assume that we know the two parameters, and we assume that we know alpha and we know beta. Again, the population intercept and the population slope. Now, since we're estimating these two parameters in order to find the degrees of freedom, we're now going to use n-2 instead of n-1. Again, because we're estimating those two parameters. Now, this is our ideal situation. Here's our population regression line, and we can see this is a relationship between our explanatory variable and our response variable. And we can see that each of the observations tends to follow normal variation here. So essentially, this population regression line, each of these points should theoretically have some type of normality. Now, the assumptions, we're used to the three big sins of AP stats, and so the assumptions here do follow those sins, but there's actually two additional ones because we are looking at linear regression, and this is where a strong understanding comes back to help us. Now, since this is linear regression, it's helpful that we use the following acronym of LINER. Now, LINER stands for linear, independent, normal, or approximately normal, equal standard deviation and variance, and random. So we already are familiar with three of these conditions. The only ones we're adding in are the linear and the equal variance. So for the first condition here for L is linear, and the overall pattern in the scatter plot of x versus y should be approximately linear, and there should be no overall curved pattern in the residual plot. So again, in the scatter, we want a pattern, and we want our residuals to rebel. We don't want any type of indicative pattern in the residual plot. Next up, for independence, this needs to be done through independent sampling. Thus, when we sample without replacement, we check the 10% condition. Now, if you are using a randomized experiment, you don't have to worry about this because of course, results will be independent since we're receiving two different treatment groups. And also thinking about this, we're not really random sampling when we do an experiment because most times we recruit volunteers to do said experiment. So that's going to be the I, or independent condition. Next up, we have the N for normality. And here, for any x value, the possible y values vary in a normal distribution. Here we check for any skewness in the graph of the residuals. Use a dot plot, a histogram, or a normal probability plot. You could also do a stem plot or a box plot if you're feeling snazzy. But we're not checking the residual plot. We're checking a graph of the residuals. So pay attention to the lingo there. But where we will check the residual plot is on our fourth condition here for equal standard deviation and variance. Here, the standard deviation of possible y's is the same for all x values. The vertical spread in the residual plot should be roughly consistent. And we can see here that we have a good example with a completely randomized pattern versus bad examples here where we can see this type of funnel or some type of curvature pattern in the residual plot. And then lastly, our very familiar condition is the random condition, which says that data should be collected using either a random sample so that we can generalize, or a randomized experiment so that we can infer cause and effect. Now, if we have these 5 conditions met, we can proceed with our inference procedure. So we're actually going to take a look here at our first inference procedure, which is the investigation as to whether or not there is a linear relationship between x and y. Since the slope represents how much y responds to changes in the x value, we can use a confidence interval to estimate whether it includes or excludes 0. If the interval excludes 0, then we can rule out the likelihood that the slope is 0. Thus, we can conclude that there is a significant linear relationship between x and y. As a reminder, x is the explanatory variable and y is the response variable. Now we're still going to carry on with our panic model for the confidence interval. Here, beta represents the true slope of the population regression line relating our explanatory variable to the response variable. We check now our 5 assumptions instead of our typical 3. We will use a one sample t-interval for slope if these conditions are met. And our following formula looks very similar to what we've done with one sample means intervals. Here, we're going to do beta plus or minus t star times the standard error of, not beta, sorry, of b, the slope. Now, b is the sample slope and SE is the standard error of the slope. And both of these values can be pulled directly from the computer output, and I'll show you how to do so in the example. And as a reminder, because we are looking at 2 parameters, our t distribution here is going to have degrees of freedom of n minus 2. And then the interpretation has not changed. We're still C% confident the interval from blank to blank captures the true slope of the population regression line relating our explanatory to our response. So let's take a look at an example here. So a college teacher or professor asked a random sample of 10 of the 250 students in her introductory statistics class to record the total amount of time in hours they spent studying for a particular test, and then combine these times with the student scores on the test. She then performed a regression analysis on the data. And below is a numerical and graphical output from her computer software. We can see a scatter plot of grade, our response, and study time, our explanatory. You can see computer output, which has our intercept, our slope, our standard errors, standard deviation, our coefficient of determination. We can see a residual plot, and then we can see a normal probability plot of the residuals. So the first result here, or question, is that if the teacher obtains a statistically significant result, can she tell her students that the data establishes that studying more will improve their grades? Why or why not? Well, no, this is an observational study or a random sample of students. Thus, we cannot infer cause and effect. We can simply infer a type of association that exists. Using the computer output, I'm able to define the model as follows. Y hat equals 62.1 plus 12x, where x is our study time in hours, and y hat is our predicted grade on the final. And I'm going to use this information now to construct a 90% confidence interval for the slope of the population regression line for predicting test score from study time. So the 2 values that I need from my computer output are the slope and then the standard error of the slope. So this is my b and this is my SE subscript b. Now I'm going to start by identifying the parameter, which here is the true slope of the population regression line relating test score and study time. So my response and my explanatory. Next up, I check my 5 assumptions here, and I saw there was a relatively linear pattern in the scatter plot, plus there was no evident pattern in the residual plot. For my independent condition, I can assume that 10 students is less than or equal to 10% of all students in the course, which is true since we have 250 students enrolled. The normality plot indicates that the normal model is appropriate, and we didn't really do too much with this, but essentially if you have a relatively linear pattern in your normality plot, you're good to proceed with the normal model because it varies using a normal distribution. The residual plot appears to show equal variance among the study times. We didn't see any evidence of fanning or any indicative pattern, so we're good there. And lastly, we did collect a random sample of 10 students. Since our conditions are met, we will use a one sample t-interval for slope. Here, degrees of freedom is n minus 2, so 10 minus 2 gives me 8. And now I just substitute in my values, 12 plus or minus, and the critical t value we'd use here is 1.86. Again, I find this from my table using 90% confidence and then 8 degrees of freedom, and that gives me 1.86, and then the standard error of the slope, which was 2.825. So here I obtain an interval between 6.75 and 17.25, which we can see is completely positive, so I have 0 is not in the interval, so I have evidence to suggest there is a positive linear relationship here. Thus, we are 90% confident the interval from 6.75 to 17.25 points per hour captures the true population LSRL slope relating study time and grade. Now, you don't technically have to include the units here because we are estimating the slope, but it is helpful to note that our slope, the change in y and the change of x. So I can expect a change in the points over the change in the hours. So that's just an example of how we would conduct a panic procedure or a one sample t-interval for the slope of a population regression line. Now, there's another example. Or are there two more examples? No, just one more example. And here we can see, is a man's height related to his weight? The regression analysis from a random sample of 26 adult men is shown. And suppose the conditions for inference have been checked and have all been verified. And typically, this is only about 5% of the AP exam, so if you do receive an inference question on the FRQs, more than likely it's going to say that the conditions have been verified, so that makes your life a little bit easier when conducting your inference procedure. So from this computer output, I can create the following LSRL model. I do my intercept plus the slope, and then I define my variables here, height and predicted weight. And the reason we go, instead of doing y equals mx plus b form like we're used to, in most real world situations, the intercept comes first, since that is the 0th value, and then the rate of change happens. So we go a little bit backwards in this course, but as statisticians, we do it the right way. Now, I'm going to construct a 98% confidence interval for the slope of the regression line. Again, I define my parameter, which here beta is the true slope of the population LSRL that relates height and weight, and I should say for men. And we were told that our conditions are met, so we can skip the A in the panic model and head to the N. We still have to explicitly label it. And just to remind the readers that we are aware that the conditions have been met, I'm going to ensure that I say, since conditions are met, I will use a one sample t interval for slope. And then my process just carries out the same. I'm going to take the slope plus or minus the critical value times the standard error of the slope. Here, degrees of freedom of n minus 2 is 24. So I take my slope plus or minus my critical value times our standard error of the slope. As a reminder, critical value times standard error. This gives us our margin of error. And thus I produce the following result of 5.47 to 12.01. So here I'm 98% confident the interval, we are 98% confident, I don't know why I put confidence, that the interval from 5.47 to 12.01 pounds per inches, again, you don't have to include the units, it is helpful. It captures the true slope of the population LSRL relating height and weight. So based on my interval alone, 0 is not included, I have some significant evidence to claim that the slope here indicates a positive linear relationship, meaning that on average, as height tends to increase, weight should also tend to increase. So that's just a little bit more information on how we inference about the slope of a population LSRL.